Hey everyone, hope I'm audible. Thanks for being here. Hi, I'm Pratyush Singhal. As introduced, I am a software engineer with Tether.io, and I work on this service mesh solution, primarily tinkering with STO nonware. Today, I wanted to talk to you about IPTables to NFTables. With the NFTables recently being GA'd in Kubernetes 1.33 release, a lot of brilliant work went behind this effort, and we'll take a look at what it means for the end users and how it supercharges a Kubernetes networking. So let's set the agenda real quick. We'll take a look at what IPTables are, how Kube-Proxy is using them, and what are the current challenges which we face in Kube-Proxy with IPTables mode. Next, we'll take a look at what NFTables brings to the table, pun intended, and then we'll see how it solves those challenges for us. And finally, we'll do a quick performance analysis between the two modes and see how they affect our data plane latency. So IPTables is the Linux built-in software firewall solution. It is built on top of the NetFilter framework exposed by the kernel. What essentially it means is that kernel exposes certain hook points in the network packet's life cycle in the kernel. And you can attach your rules for filtering and NAT to these hook points. So you can add your rules to different tables and chains which are attached to these different network hooks and do whatever network manipulation you want to do. Now, Kube-Proxy uses these IP-table rules to configure service routing. Let's take this example. You have two services, two pod endpoints backing each of these services. Now, Kube-Proxy will monitor all these events from the API server, convert all of that information into an IP-table rule set, and apply it across your node, which basically means a couple of service chains, pod endpoint chains for your final routing. So in this example, IPTables actually adds a rule in the Kube services chain for your destination IP 10.255.0.1, which is the cluster IP of service A. So basically, any network packet which is destined for 10.255.0.1, the service A's cluster IP, protocol TCP at the destination port 80 is routed to a service-specific chain, from where it is again routed to an endpoint-specific chain, and finally, destination NATed to our pod endpoint. Now, IPTables is the default mode and has built this foundation of service routing for us. IPTables is great, but why are we moving away from it? So IPTables was never meant to handle the Kubernetes type of scale. There are a couple of challenges which we face with IPTables. One, there is no support for incremental updates. So whenever you have to make a change to any rule, let's say a service came up or a pod endpoint went down, you have to acquire a node-wide lock, update the rules, then upload the entire rule set back to the kernel, and then release the lock. This global locking leads to a significant impact in the data plane programming latency for Kube-Proxy, which basically means the time it takes for Kube-Proxy to set up all these IP-table rules on your nodes. Next is the service chain match, which is the sequential search match. Now, in our previous example, we had a Kube services chain and a bunch of match rules for network packets destined to different services. Now, whenever a network packet comes in, IPTables has to sequentially match through this list, find the rule which matches that particular network packet, then route it to the service-specific chain. Now, as you have more services in your cluster, the average first packet latency gets affected, which is essentially O of n, where n is the number of services in your cluster. Now, as your cluster grows, you have more services, more applications, more deployments, pods, and endpoints. The number of rules in your cluster increases, which further amplifies the effect of the first point, that is, lack of incremental updates lead to significant impact on your data plane programming latency. And because of this sequential search, your first packet latency also takes a hit. Next, IPTables is also not very suitable for multiple users. Let's say you have multiple components which are trying to update these IP-table rules. What ends up happening is they do not have to just fight over the ordering, but they also have to fight over this global lock, with IPTables being the shared resource. This lock contention leads to a noisy neighbor problem in your cluster. Now, a common example for this is CNIs like Calico, which have to modify IP-table rules alongside Kube-Proxy. Next, IPTables was written a long time back, and it is officially a legacy technology now. So development for it has mostly stopped, and all the new fixes and features are making their way into NFTables instead. For example, IPTables is meant for deprecation in Red Hat Enterprise Linux 9, and it's planned for removal with the version 10. So IPTables does face a couple of challenges when we are trying to use it with Kube-Proxy. Now let's welcome NFTables. So NFTables is the successor for IPTables in the Linux kernel. It is built over the same NetFilter framework, which allows you to attach your chains, or essentially your rules, to the same NetFilter hooks we are already familiar with IPTables, pre-routing, input, output, etc. Next, it allows each component to have different tables and chains. Now, each component can manage their own rule sets without stepping on each other's toes. It also introduces a much simpler and compact API, which I feel is a big win. So when I started diving into Kubernetes networking landscape, right, IPTables was a very intimidating thing. So NFTables is a big win over that, makes it much more readable for you. Now, let's come to the interesting bits. NFTables supports dynamic rule set updates and introduces this concept called verdict maps. With dynamic rule set updates, we no longer need global locking, and there are no noisy neighbor issues. Now, each component can manage their own rule sets without fighting for the global lock and not introducing a noisy neighbor problem in your cluster. With verdict maps, which are essentially a map for you to match your service chain and give out an action or verdict in return. These turn our ON service chain lookups to O1, which significantly improves our first packet latency. So let's take a look at what it means in the new rules. So first, Kube-Proxy defines a NAT pre-routing chain, attaches it to a NetFilter pre-routing hook, sets a custom priority for it, and adds a rule to jump to the custom services chain. This custom services chain is again registered by Kube-Proxy and looks something like this. So in the services chain defined by the Kube-Proxy, we first build a lookup key, which is made out of the network packet. You take the destination address from the network packet, which protocol is used, and what is the destination port. You build a lookup key from this and look it up in the service IP's verdict map. So now let's take a look what this verdict map is. So first, we define the type of the verdict map. We have our key, the concatenated IPv4 address, protocol, and the service port, with the value, which is the verdict. That is the action that NFTable needs to make for handling your network packet. Then you have your self-describing comments, making it much more easier to understand what different map and sets are all about. Then finally come your elements. So now if we have a packet which is destined for 10.96.34.36 using protocol TCP at 9080, NFTables directly knows what action it needs to take. That go to this service-specific chain. From there, it is finally routed to your pod endpoints. So enough chit-chat for the day. Let's talk numbers now. So we'll compare the first packet round-trip time, which is the time it takes for the first response packet to arrive back at the client after it makes a request. Now, the data I'll be presenting here was computed as part of the talk From Observability to Performance in KubeCon NA 2024. I highly recommend everyone to give it a watch if they want to understand how these numbers are computed and how the SIG networking team has actually benchmarked the two modes. So let's take a look at the first packet round-trip time for IPTables mode. Now, as expected, because of the sequential search, as the number of services in our clusters grow, so does the data plane latency, which is essentially the first packet round-trip time, grows linearly. Now, these are different quantiles where P50 is the mean latency for us, and P99 is the worst 1% latency we see in our cluster. Now let's compare it to NFTables. In NFTables, because of the verdict maps, which allow us the O1 lookups, we now have consistent latency numbers as the number of services grow in our cluster. If you can see that in all the quantiles, we can see the results stay more or less consistent. Now, the interesting thing happens when we actually put these numbers side by side. I hope everyone can see that IPTable forms a peak at 30,000 services, where NFTables not only stays consistent with the increasing number of services, it performs equivalent or better than IPTables mode. And it's a big performance improvement. So it's a big performance improvement, great. So should you jump to NFTables mode? Now before you do that, you should stop, and there are a couple of things you should consider. One, it requires a new Linux kernel, and I know how hard OS patches are. It is still new, and it is not as battle tested in large-scale production settings as IPTables mode has been. You also need to ensure compatibility with your existing networking and observability tool stacks, but the ecosystem is catching up fast. And you need to be aware that there are slight change of behaviors which are introduced between IPTables and NFTables mode. Although the community tries to be as much backward compatible as it can, and even here that's what they're trying to do, these changes are not treated as backward incompatible. The reason being, Kube-Proxy's IPTables mode still remains the default, and NFTables mode is something which you have to opt in. So what you should do? You should try it out for yourself. You can currently try it out using Kind, KubeADM, AWS EKS, depending on your preferences. All of them allow you to configure Kube-Proxy in different modes based on your requirements. You can compare the results in your environment and see how it works for your applications and your infrastructure. So in conclusion, IPTables is great. It has been the industry standard for a long time, and it has built the foundation for Kubernetes. But I think it's now the time we start stepping away from it. NFTables tries to build over it. It is the official successor for IPTables, and it's already proving to be a big improvement. Now, before you upgrade, you should obviously thoroughly test it out in your development and staging environments, and be aware that there are slight caveats you should consider. Now, NFTables is currently under active development. There are a bunch of exciting new features going to be coming with each future release. So as always, provide your valuable feedback to the networking team and let the community do its magic. Thank you. That's all, folks. Let me know if you have any questions. Or if everything went above your head, that's totally fine. You can ask me to repeat as well.